In this lesson, we're going to look at something called Pascal's triangle and the binomial theorem. We're going to see how it relates to the binomial theorem. You may have come across Pascal's triangle before, but in case you haven't, here's how it works. It's this relationship between numbers. I don't like how this 1 is off to the right a little. I'm going to put it right here in the middle. So just focus on the triangle for a second. So we start with 1 in this top row, and then we got 1 and 1 in the second row. From there, we can get any number in the future rows by adding two numbers together. So if I add 1 and 1 together, that gives me 2. That's where that number comes from. And if I add 2 and 1 together, that gives me 3. And 3 and 1 gives me 4. And 3 and 3 gives me 6, and so on. So as far as the triangle goes, to get any number, we add the two numbers that are above it. And so it's slightly offset so that we can have the numbers in between like that. You'll notice that on the outsides, we have only one. We always have 1 running up and down the outsides because there aren't two numbers above any of the outside numbers that would allow us to add them together. So, I mean, there's no number over here for me to get the 1. So it's just, I could think of it like I'm adding nothing to 1 to get the 1 below it, but it's always going to be 1 on the outside. So that's the pattern for Pascal's triangle. So if I wanted to carry on and fill in the next row, it would be 1 on the outside, and then I'd have 1 and 4 gives me 5, and then 4 and 6 gives me 10, 6 and 4 gives me 10 again, 4 and 1 is 5, and 1 on the outside. And then the sixth row, 1 on the outside, 1 and 5 would give me 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 6 and 1. So we could keep going. There's nothing saying that we have to stop on the 6th row. That's just as far as we've gone right here. In fact, at the end of this note, you can see we've got, what do we have here? 19 rows, I think, of Pascal. No, 18 rows of Pascal's triangle. I can tell because the last number here is 17, and so we're actually always have 1 more than that number here. So there's 18 rows shown, and they're all being created the same way. So, for example, that 6th row I just did, which went 1, 6, 15, 20, 15, 6, 1, there it is. The next row would be 1, 7, 21, and so on. So, and I could keep going beyond that as well. Again, there's no reason why we had to stop there other than maybe lack of space. So that's Pascal's triangle. It's got a lot of interesting features about it. First off, notice how we've numbered the rows down the left-hand side, but we don't start with row 1. The top row is actually called row 0. I hate the way my iPad jumps around when I undo something sometimes. Anyway, this top row is called the 0th row. That's going to come in handy if you ever do stuff with something called combinations. It's not part of this math course. If you take data management, a grade 12 course, then you will learn a bit about combinations. But that's not in this course. Anyway, why do we call the first row the 0th row? So that we can do other math with it that's not part of this course. So just take it as given for now that this is the 0th row here, and this is the first row, and this is the second row, and so on. We also number the terms within the row. This would be the 0th term in the 0th row. So carrying on from sequences, where we talk about terms, we can talk about term 1. I can actually number a term in this row by both the row number, it's the 0th row, and the 0th term. Whereas this one here would be the first row and the 0th term. Whereas this one would be the first row and the first term. So again, we start counting at the term number 0. This is the second row and the 0th term, second row and the first term, second row and the second term, and so on. Again, not a big deal for what we're doing here, but it is good to understand just where the numbering is going. So the first element in any row is considered to be the 0th element, as I pointed out. So these are all the 0th elements here. 0th, right? The first row is considered the 0th row, as I pointed out up here. Pascal's method, I just explained it. To determine any value, add the two values above it. The sum of the elements in any nth row will be 2 to the n. So if I wanted to add up, getting back to this idea of series, say I wanted to know what this was, add them all up. Well, I could add them up. 6, 10, 16, 26, 31, 32. But that's equal to 2 to the n. N is the row number. So that's going to be equal to 2 to the 5. 2 to the 5 equals 32. So I know what the sum of any row is just by doing 2 to that exponent. So that lets me know that the sum of all the numbers in the 6th row is going to be 2 to the 6, or 64. And you can double check that if you wish. So that's Pascal's triangle, just a quick and dirty overview of it. Not getting too much in depth with it, but the basics of it. The reason that we're learning about it is actually so we can use it for something called a binomial expansion. And that's the next part we're looking at here. So we're going to forget about Pascal for a minute and just do a little bit of expanding. So this first one here, we've got a plus b, that's a binomial, to the exponent 0. We know that anything to the exponent 0 equals 1. So it doesn't matter that it's a binomial, it's a, it's b, whatever. If it's to the exponent 0, and this whole bracket here is to the exponent 0, it's equal to 1. This next one, we know that anything to the exponent 1 is just itself. So a plus b to the 1 is just going to be ab. Now this next one, we know that anything to the exponent 2, if it's on this bracket, this 2 is on this whole bracket. So we're going to multiply it by itself. So it's going to be a plus b. Not sure how my color changed. Let's go back to blue. A plus b times a plus b. We're going to use FOIL. And when I do FOIL, I'm going to do a times a and a times b, which gives me a squared plus ab. And then I'm going to do b times a and b times b. B times a is just ab. I'm going to put it in alphabetical order still. So even though I did b times a, I'm going to write it as ab. And b times b is b squared. And then if I collect my like terms, I've got a squared plus 2ab's, right? I've got ab plus ab, which is 2ab plus b squared. So that one was a little bit harder. Maybe we'll just circle our answers as we go along. So we got 1, very nice, a plus b, yeah. And a squared plus 2ab plus b squared, getting a little bit tougher to do. Now we're being asked to do, Now we're being asked to do in this one, a plus b cubed. So that literally means a plus b times a plus b times a plus b. It's starting to get a bit tedious, isn't it? Luckily, we already know what a plus b times a plus b is, so we can do a little bit of a shortcut. So say I wanted to think of this as a plus b plus a plus b I want to use. I could use my answer from here to replace this, since that's what we just did. And then I'd have a plus b times a squared plus 2ab plus b squared. And then I'd have to do the distributive law on this. I'm going to have to do a times each one of these terms. And then I'd have to do b times each one of these terms. And I can do it, although it's definitely getting a bit more tedious, isn't it? If I do the first one, I'd get a cubed plus 2a squared b plus a b squared. And then the green ones from underneath, from doing the b, I'd have a squared b plus 2ab squared plus b cubed. And then I'd have to collect my like terms. So I'm just going to write underneath here and pretend that line isn't there. And collecting my like terms, I'm starting with my highest a's, I got a cubed. And then I'll go to my a squareds next. So I've got an a squared there, and I got another a squared there. So a squared b gives me, plus 2a squared b gives me 3a squared b. Then I'll move on to my just a's with no exponent on it. So I got an ab squared there, and I got another 2ab squared. So when I add those together, I got 3ab squared. And then finally, I've got my b cubed. So when I combine all my like terms, I've got this one. That was definitely more work. And I even made it a bit easier by taking my answer from a plus b squared to help me out. So look at the answers to the 4 expansions. Do you see a pattern? Well, look at the coefficients in particular. In the first one, now there's a lot of colors going on here, so it's hard to make any one thing pop out. I'm going to use purple. In the first one, I got the number 1. In the second one, let's put coefficients in front of the 1 and the b. I got 1 and 1. And again, let's put coefficients in the third one in front of the a squared and the b. Then I got 1, 2, 1. And if I put coefficients in the third one, a cubed, and 1 in front of the b cubed, I've got 1, 3, 3, 1. Those numbers might ring a bell. They correspond to the first 4 rows of Pascal's triangle. All right, we had 1, we had 1, 1, we had 1, 2, 1, and we had 1, 3, 3, 1, which is what I just highlighted in these 3 examples. 1, 3, 3, 1. So that's the expansion of a plus b cubed. So maybe we can already start to see why we number the rows the way we do, because this 3 here corresponds to row 3, right? Row 3, third row, actually has the 4 numbers 1, 3, 3, 1, whereas row 0 just had the number 1. And so again, numbering, starting counting at 0, corresponds to the rows, the coefficients, and the rows of Pascal's triangle. So if that's the case, then I can use Pascal's triangle to do the following expansion. I know that I'm going to have the numbers 1, 4, 6, 4, 1 for row 4. So if I write those out first, 1, 4, 6, 4, 1. Then let's look at the pattern of the letters. I've got A's, right? I got a cubed, a squared, a, and then there's no a in the last one. And a cubed matched up with the 3 of row 3. So it seems like if I start with a and whatever my exponent is, in this case it's a 4, and then go down from there, a3, a2, a, and then no a in the last one, then that should cover off my a's. And then as far as the b's go, there's no b in the first one, but then there's a b here, b squared, b cubed, and so it goes up to, again, this number that was the exponent on my original question. So I can start with no b in my first term, then go b squared, b cubed, and then b to the 4, because I'm going up to 4 in this case. Put plus signs between each of them, and there is actually my expansion of a plus b to the 4. So I got what a plus b to the 4 is equal to, so I know what this is equal to without having to go through the extreme pain of having to expand out 4 different brackets, each with a plus b in them, and multiply them together. And it's going to save me even a bit more trouble when I do a plus b to the 5. So what's the next row? It goes 1, 5, 10, 10, 5, 1, because we're starting with the exponent 5. So 1, 5, 10, 10, 5, 1 was the coefficients. I start with a to the 5 and go down from there. Remembering there's no a in the last term. I start with b to no b in the first term and go up from there, b to the 1, b2, b3, b4, b5, put plus signs between them all, and that is certainly a much quicker way to expand a plus b to the 5 than having to do all that multiplication and FOIL and stuff like that. So that's nice, right? That's a real time saver. But what if I don't have just a plus b that I want to multiply together? What if there's numbers and negatives and other things in there? Well, we're going to see a couple of examples of that. So that's actually just, hopefully you got the idea, and let's just look at an example. So look at this first example. Instead of a and b, we've got x and 2. So x is like my a value, 2 is like my b value. Otherwise, it's exactly the same as what we just did in this one right here. Here. It's going to be exactly the same. I'm going to do this, what I just did here, except instead of a, I'm going to write x. Instead of b, I'm going to write 2. And it's going to require a bit more simplification because of that number 2 is a number instead of another variable. But let's see what we can do. We got this exponent 5, which means row 5 of Pascal's triangle. So my coefficients are going to be 1, 5, 10, 10, 5, and 1. Instead of starting with a as my highest exponent, I'm going to start with x. My highest exponent is 5. So x to the 5 and go down. 4, x to the 3, 2, x to the 1, and no x. And then I'm going to have 2, and I'm going to go up. So no 2 in the first term, but I'm going to have 2 to the 1. And this is all multiplied together. So in order to show that this is a multiplied by a 2, I am going to put it in brackets. So 2 to the 1, 2 squared, and I'm going to just keep increasing the exponent on the 2 until I get up to 5. And then plus signs in between them. And so that's just our expansion. I am going to have to simplify things because of the fact that I wouldn't want to leave all these 2's and just untidy numbers here and there. I want to collect my like terms and simplify. But before I do that, let me point something out. Look at the exponents here. 3 and 2, that equals 5. So does 2 and 3. This one here is a 5. This one here is a 5. Even this one, when you consider that if there's no exponent written, there seems to be a 2 on the 1, and there's no exponent over on this side, there's a 1 on the 2, and there's a 1 on the x. When I add up all the exponents, whether they're actually written or just implied, they always add up to 5. They're always going to add up to whatever the exponent is on the original brackets. So that's a good way to check something that you've just done. Anyway, so that was just an aside. Let's tidy up here. I don't need to write the 1 in front of the x to the 5. And I know that 2 times 5 equals 10. So I should write that as a 10 and just put that out front. Write that as 10x to the 4. I know that 2 squared is 4, and 4 times 10 is 40. So I should just write that as 40x cubed. And 2 cubed is 8. 8 times 10 is 80. So I should write that as 80x squared. 2 to the 4 is 16. And 16 times 5 is 80, so that's 80x. And then 2 to the 5 is 32, and 32 times 1 is just 32, isn't it? So there's my final answer. Again, the highlighting is just showing where things come from. Obviously, the highlighting is not part of the answer. It's just letting you see where stuff comes from. So my answer to x plus 2 to the 5 is x to the 5 plus 10 times x to the 4 plus 40 times x cubed plus 80x squared plus 80x plus 32. That's all we do. All that changes from one to the next is what am I going to let my a value be and what's going to be my b value. In this case, a is 2x and b is negative 5. And it's to the exponent 4 this time. So remember, for the fourth row of Pascal's triangle, it went 1, 4, 6, 4, 1. Did I space those out enough? Maybe I should space them out a bit more. Okay. So if A is 2x, I'm going to have 2x to the 4. Then I'm going to have 2x to the 3. And I'm going to go down with my exponent each time from there until I don't have one for the last term. If b is negative 5, I'm not going to put it in the first term, but I'm going to start with negative 5 to the 1, and I'm going to go up with my exponent from there. Again, check the exponents. When I add them together, they always add up to 4. Again, assuming that there's a 1 assumed to be on the negative 5 here and on the positive 2x here as my bases. Right, like this. So they always add up to the 4. Put plus signs in between and simplify. So we have to remember our exponent laws. 2x to the 4, I have to apply that exponent 4 to the 2 and to the x. So 2 to the 4 is actually equal to 16, and 16 times 1 is still 16. So I get 16x to the 4. I'm going to apply the 3 to the 2 and to the x. So 2 to the 3 is 8. 8 times 4 is 32. But I also have to multiply that times negative 5. So maybe I shouldn't show too much in one step. Why don't I just, rather than collecting things up for now, I'll just expand them. So 4 times 8x to the 3 and negative 5 to the 1 is just negative 5. And I'll do another step to gather up my coefficients. Then I've got 6, and again, 2 to the exponent 2 and 2 to the x gives me 4x squared. And negative 5 squared is going to be positive 25. And then I've got 4 times 2x, because that's just to the exponent 1. But negative 5 cubed is going to be negative 125. And finally, negative 5 to the exponent 4 is going to be positive 625 times 1 is still positive 625. So I expanded out with the exponents, but now I still have to collect my numbers up. 16x to the 4 stays the same, but if I multiply 4 times 8 times negative 5 together, I get negative 160. So I write this as negative 160x cubed. And then if I do 6 times 4 times 25, I get 600. $600x squared. And then if I do 4 times 2 times negative 125, I guess that's negative 2,000 x. And then I still got the 625. So that's where they came from. Again, maybe let's get rid of the highlighting so that it looks a little more traditional. There's my expansion there without the highlighting, but you can see a lot of the work was using the exponents to add up the to apply to each part, and then I have to multiply them together, and I have to be really careful about signs too. That negative 5 caused all the signs to oscillate back and forth between positive, negative, positive, negative, positive, negative. So if I've got a negative in there, the signs are going to go back and forth like they did in this case. Okay, one more example. This one's got a 3 out front, It's got an x squared. It's got all kinds of stuff going on. The 3 is just, again, we have to follow order of operations. So the 3 is going to come later. For now, all we have to worry about is that a value is like x squared, and b is negative 2x. And my exponent is 4, of course. So, fourth row of Pascal's triangle goes 1, 4, 6, 4, 1. And if a is x squared, I'm going to have x squared to the 4, right? I take my a value and raise it to whatever that exponent is. And then the next one would be my a value, which is x squared to the 3. And so, again, it goes down by 1 each time. And then there's no x squared in the last term. Then I've got negative 2x. And again, it's not in the first term, but for the next one, it's negative 2x to the 1, negative 2x to the 2, negative 2x to the 3, negative 2x to the 4. Plus signs, and then a whole whack of simplification. Oh, and whatever happened to that 3? Well, I guess what I should do, I'm really multiplying everything by 3. I should throw some brackets around this, put the 3 out front, and then at the end I'll just triple all my coefficients. So let's start with that. I'll just put the 3, put a bracket here to remind myself, and then go from here. Exponent laws, power of a power, multiply the exponents, that just becomes x to the 8. Again, power of a power. So I'm going to do this in a couple steps again. So I got 4. This is going to become x to the 6. But I also have this negative 2x going on here. And then the next one, I've got 6, and I've got x to the 4. And I've got, again, I have to distribute this exponent 2. Negative 2 squared is positive 4. X squared. So I'm going to have to be doing even more collecting of terms in a moment, but that can be for our next line. 4 x squared, and this one is going to become negative 8 x cubed. And the last one is going to be positive 16x4 times 1, which is still just positive 16x to the 4. End bracket. All right. We're on a roll. Let's see what we can do now. Let's write the 3 down again. X to the 8, nothing to do with that. All right, now I need to multiply my coefficients together. 4 times negative 2 gives me negative 8. X to the 6 times x, I'm multiplying powers of the same base. I add the exponents. So I'm going to have x to the 7 from multiplying those two guys together. Then I have 6 times 4. That's 24. And I've got x to the 4 times x squared. That becomes x to the 6. And then I've got 4 times negative 8. That's negative 32. And I've got x squared times x to the 3. That becomes x to the 5. And finally, I've still just got 16x to the 4. Nothing really changed there. And now that I've actually simplified it down, but the final step is distributive law. I have to multiply 3 times each one of these numbers here so that I can take these brackets off. So I end up with 3x to the 8 minus 24x to the 7 plus 72x 6 minus 96x to the 5 plus 48x to the 4. And that was a lot of work, I'm not going to lie. But it was a heck of a lot less work than if I'd tried to do an expansion on it just using FOIL and polynomial multiplication.